Okay, so this is lecture 35. Just see if the marking comes okay. Anything is there, let me know. Okay. So in the last lecture, we basically were looking at the CML output driver. Okay. And in the very last, it was pointed out that can we do something different to the CML output driver at the load side, which is that in the, like right now we are using a resistive load in this particular design, but so this one is your, let me just mark these as two different channels. Okay, so this is equal to RT, which is equals to where Z0 is equals to RT, right? So it was suggested that can we replace this RT resistance with an active load, which means can I do something like this? I can use a PMOS load with a differential termination to RT and everything else remains the same. Okay, so this is theoretically possible, but what happens is if you are having any PMOS as a current source here, right, and a bottom current source, first you will need a common mode feedback to fix the bias voltage. Let's say that is VBP, you can still fix it. But the problem happens that you are losing the overdrive you're losing a voltage which is equal to the overdrive of this PMOS transistor for your swing. So in the previous case, what you have only a NMOS as a current source and two input pair. Rest of all from VDD to rest the output is basically available for you for the swing. But as soon as you start using the current source at the top and bottom, you will lose that margin. And the other thing is not only that you will lose the margin at an operating point, also think about when both these nodes are swinging up and down, and what will happen to these current sources. A very special case of this is, I think this you would have heard of it, is LVDS signaling, right? Where you have a PMOS current source and then you are having a PMOS signaling. It's like just whatever you are seeing at the bottom, you just see the same thing at the top. So in this particular case, the only problem is that the available swing which you get is actually lesser. Okay, so this is not, and the other problem also will be when you are having too many capacitors, then you have too many transistors under a single supply. You have more capacitors to be charged and discharged when you are signaling the whole chain. So the thing is, the actual speed which you can get with this LVDS output driver is actually lesser than what you can get with the very simple CML output driver. Okay, so now the other case is, the one which we have seen is actually with a single-ended termination on both the load and the source side. The other case is where I have a differential signaling. So it has its own benefits that, so let's say you are having channel and in place of connecting it to any VDD, you connect with itself. So this is both RT and RT. So you can say these output nodes are VOP TX and this will be VOP RX. Okay, so in this particular case, you do not have any bias current which is flowing through the channel because they are connected between the same output common mode. Okay, the benefit is you do not need to maintain any specific voltage on the receiver side, right? But the problem is that you have only differential termination on the receiver side. You do not have any common mode termination. So if there are any common mode reflections, then that will basically degrade the signal swing at the output. And in this case, the receiver, if you are basically having any receiving amplifier, that should work at the common mode at the receiver side. So you are fixing the common mode on the receiver side by fixing the common mode on the transmitter side. If you want to work with any different common mode, either you use a AC coupling in the path, or you have some kind of level shifting which you use on the receiver side. So both the things are very much utilized. Another problem with this is, okay, so look at it in a more simpler manner. Let's say when Dn is equals to 1, okay, so when Dn is equals to 1, then your M1 is on and M2 is off. Okay, so now look at the current flow. This is very important where it differs from your common mode signaling. So this one is RT. If this is, so let's say there was a current source which was I0. So the I0 current will still flow because you are steering all the current. So I0 current is flowing through M1 now. Okay, and then this node which is basically terminated on the other side and the other node, right? So you have a 2RT resistor effectively here, and this is VDD. Okay, so now see that if I call this as a VOPTX node and VONTX, so can you tell me what is the current which is flowing through the left RT? Just by simply because you know the resistors, right? 3/4 RT, right? So VONTX is equals to VDD minus 3/4 I0 into RT. Okay, and VOPTX is equals to VDD minus I0 by 4 RT, right? So the current is actually, if you see the current which is flowing on the right branch is something kind of like this, right? It's coming from the VDD on the right transistor and flows it. So if I want to see VOPTX minus VONTX, which is equals to I0 by 2 times RT. So the signal swing is the same which you are getting with the common mode termination. The only difference is the current which is flowing through the output, the termination resistor on the receiver side is I0 by 4. This has the consequence that if you look at both these potentials VON and VOP, right? In the previous case where you had a common mode termination, in that case VONTX means, if I just want to remind you, so one thing was that VOPTX was going to VDD, right? And VDD whatever, let's say it's the same VDD, and VOTNX was going to VDDTX minus I0 by 2 RT. That's how you are getting the same swing. So depending on the swing at VONTX and VOPTX, which design do you think will basically stress the input pair more? A common mode termination or a differential mode termination? So when I say it stress the input pair more, that means the VDS on the input pair is actually lesser. That way is going to stress the design more, right? Did you get my question? So you see that in both the cases, for the common mode or a differential mode termination, the final differential output swing is more. But the individual potentials on VOPTX and VONTX are different. So which particular design will basically stress your input pair with a smaller VDS? Differential termination. So this is one of the drawback with the differential termination. And if you want to have a very large swings, then you are going to crush the input pair more. So you have to take care of it when you are doing this particular. The other important takeaway from this differential termination is that you see, in order to produce a swing of I0 by 2 RT across the receive, the current requirement is minimum, right? Minimum current for this output swing is equals to I naught by 4. So I naught by 4 is the minimum current which you are passing through the load transistor to generate the swing I naught by 2 RT, and you cannot basically have any current lesser than that to produce the same output swing. Does everyone recognize this basically thing? The minimum current to produce a swing across a 2 RT transistor is I naught by 4. Okay, but in this particular current mode output driver, we are burning I naught current because of the design which we are having. Okay, so this you can so this is the very basic of a voltage mode output driver. That in a voltage mode output driver, the minimum current consumption is the current consumption is 1/4 of the current consumption in a current mode output driver. And you can very well think in this manner that the minimum current required to produce the same swing is only I naught by 4. So we will go into that voltage mode output driver later, but this is how you can think about it. Okay. So the next thing is that, so we know that how the common mode current mode output driver works. Now the other one is CML based equalization. Okay. So in a CML based equalization, yeah. Pardon? This is a current mode output driver. So the thing is, the current mode output driver tells that means this is just one implementation, right? It tells that in order to produce a swing of I naught by 2 RT across the 2 RT of the termination resistance on the receiver side, you only need a I naught by 4 current. No, this is, you are considering 2 RT because this is a differential output driver. So you are having a differential termination on the receiver side. That's why the 2 RT will come in. If you are considering only a single-ended termination, that is only a RT resistance. Does that clear your doubt? No, what? Can you just repeat the question then? Differential termination is 2 RT. How differential termination on the receiver side is RT? Okay, so let's look at this. Differential termination means, so okay, let's say you are having 2 channels, right? So if you look at the impedance, let's say what is equals to G naught RT, the same. Okay. Now in this case, let's say I am having a resistance RT on each side, and I am applying a differential signal, which is basically something as V in by 2 and minus V in by 2. Okay, so on the receiver side, you see the very receiver terminal, let's call it as X terminal, right? That is terminated with a resistance RT. It is terminated as a single-ended manner. Okay, now let's consider another where in this particular case, right? So if I apply a differential signal, okay, for a differential signal you can say I am having equivalently RT and RT with a common mode here, which is incrementally 0. So both the channels are terminated with the resistance RT for differential signals. But if I apply a common mode signal, will that be terminated? Yeah. So that will be a different termination. So when you are considering the output, when I am taking a 2RT, that 2RT is considering the termination which you are seeing here. Okay. Fine. So, okay, so we are looking for the CML equalizer where, so let's consider your H of equalizer of Z as simply like 1 minus alpha Z inverse. Okay, so let's not use 1 minus alpha, let me just use what are, okay, so I use alpha naught plus alpha 1 Z inverse. This is the equalization which I want to implement with the current mode output driver. The way to go ahead is that I use one which is controlled by Dn, another which is controlled by Dn minus 1, and this we can generate with the flip-flops. Okay, and let's say these are all differential signals. So you are having this resistance and it is added with a proper polarity, for example here, and okay, so now each cell is your input pair which is I, and this can be Dn and Dn minus 1. Okay, so each block is this input pair. Now if I want to implement equalization with the weight, so if let's write just the output swing if we are considering this way, this implementation. So this is, let's say, VOP and VON. So VOP minus VON in this case, and let me just call this as so say I main times Dn plus or minus I post cursor times Dn minus 1 times RT by 2. So I am just writing whatever we have seen, that the output swing for the previous case is equals to I naught into RT by 2, where I naught is the current in the tail current source. So if I just say that for the main cursor, which is Dn, the current is the I main, and for the post cursor this is I post, and so the output swing will be like in this manner. Okay, now this particular thing can be written as, let's say, I main plus I post times RT by 2, and I have, let's just call this as I naught Dn. Here I am considering that Dn are like plus minus 1 rather than 1 and 0. So I post by I naught. Let's use the same terminology. I naught Dn minus I post by I naught Dn. Okay, so I naught, this whole thing I naught into RT by 2 is the maximum swing. Okay, so what I can say, let's say I naught into RT by 2, and I main by I naught can be alpha naught Dn minus alpha 1 Dn minus 1. So using these current weights, I can very well basically realize the coefficient. Now the thing is, you do not know to begin with what should be alpha naught and alpha 1 be. So the initial thing what we can say is, I want to realize I main, which can be anywhere between 0 to I naught, and similarly I post anywhere between 0 to I naught. So if I have a full freedom for the current to change, I can realize any coefficient in this case, right? Now The thing is, how will you change the current as such? So the easiest thing which you can say, that you can change the current by changing the current source, which is shown here. You can change VB potential, just the bias thing, and you can change the current source. The problem will come if you realize all the current change by using, like, you can think you are going from a zero current to the maximum current, depending on the requirement. So if you consider that, say, the main cursor is working for a 3I/4 current, just for example, I main is equals to 3/4 I naught, and I post is equals to I naught by 4. So the thing is, as the gate overdrive of this current source will change, the operating means the source potential of the input pair will change, and you get more data dependency at the output. Okay, so the thing is, you do not want to have this kind of data dependency. You can always say, you can, whatever the data dependency you are getting, you can equalize with this equalizer itself, but you are like not, you are like using the equalizer strength to equalize the circuit rather than equalize the channel. So the better way would be that whatever the resolution of the coefficient we want, let's say if I want to change the current by a resolution of I naught by 32, just an example. So what I will go and do is, I will make a cell which carries only I naught by 32 current, and the input pair is also sized in that particular manner. So just for example, let's say I say this is W by 32. So I will use 32 such cells to realize one main cursor and one post cursor, and depending on whatever resolution I want, I can change it. Like I can choose 16 here, 16 there, or in this manner. Now if you look, that this is the case only with the one post cursor and one main cursor. As your number of taps increases, you will just keep on increasing this 32x if you want that resolution with the full freedom, right? What will that do? That is actually going to increase your capacitance looking at this node. So you keep on increasing the number of taps, you will keep on multiplying, like everything becomes, for example, 32x and 32x, and more will come. So that will increase the capacitance at the output, which will again lower the bandwidth of the system. Okay. Then the other problem is that for each cell, yeah. Why? So okay, so if you do not scale the differential pair, if you only scale the current source, right? So your differential pair will be working with means you will design it for the maximum current, so that it should be able to carry the maximum current. Now think that, let's say the post cursor is working with only minimum current, just for example, I naught by 32. Okay, and the main cursor is working with 31 times I naught by 32. In that case, the input pair is working with a different VDS. Sorry, the input pair for the post cursor is working with different VDS than the input pair for the main cursor. Okay, this will introduce the data dependency at the transition points. So because, okay, so the thing is, if you consider everything ideal, this will not change anything. But when you start considering the capacitance at different nodes within the circuit, which are switching with different potential, they will introduce a data dependency at the output. So if you want any uniformity, whether you use one cell or two cell, if you want the uniformity, you use it the way like everything is uniformly segmented. Okay. So the problem with this uniform segmentation is that if you, let's say you use 32 cells, and let me just, so if you want to switch off any of these cells, right? So I think previously I have talked that you have a CML output driver, which is basically preceded by a pre-driver, okay, and which is then preceded by your CMOS to CML converter. This is one CML output driver cell. So the thing is, at what level of segmentation do you want? If I just means if I make everything as a uniformly segmented, the CMOS to CML output driver, the pre-driver and everything, that is a much more segmentation, and that will cause you to spend more power because you are having now more parasitics in the path. Okay, so the way is that, okay, I will get it back. So way do is that you do one kind of like a binary segmentation and then a unithermometer segmentation. That is that I use a output driver let's say this is 8x, then I use a pre-driver which drives a 8x directly. So this is like, sorry, this is only a single driver. And then you have a CMOS to CML converter. So this is one cell. And if I want to realize a 32x of the 32x size for the precursor, I will use 4 of these. Okay, but if I keep everything as a uniform segmented, it is still adds an overhead. Whenever any cursor tap comes in, I need to spend 4 for that. So we do not do that. What we do, we can use a mux here. So each cell can have a mux which is having dn and dn minus 1, and you have a select signal which will basically make the branch selecting between the dn and dn minus 1, because the final output swing is, maximum output swing is fixed. Okay, so if I use total, this is 4, right? So let me just call this as CML equalizer cell, okay, and I use 4 such CML equalizer cell which are selecting between dn and dn minus 1 independently. So okay, so in this case you actually limit the hardware to a lesser hardware, minimum hardware, that the total current you still see is equals to 32x in all the 4 branches. You split this 32 unit cells between the dn and dn minus 1, and all these are added to the same. So these are all differential, so let's see only as a single ended. So they are all adding to a resistor, output driver resistor. So this resistor is only one, which is the termination. Now if you do it in this particular manner, you are reducing the parasitics, but the problem is your resolution has gone bad. And how the resolution has gone bad, see this, that this is a 8x cell, right? If I want to realize, let's say for example, post cursor is only 3 cells. For example, but I select the whole branch for dn, I can select either for dn minus 1 or dn. If I select for this as a dn minus 1, then I am using post cursor as only 3 cells, and the rest can go to the DN. So that is like the main cursor is 24 cells. Okay. Ideally, if I would have want this split this uniformly, I would have got the weight like the I post by I main as 3 by 32. But now I can get only 3 by 24. So what you can do is, or what is normally done is that one cell is actually fully dedicated to the post cursor and the main cursor. That is that I will have one cell with always with DN. I will use, depending on how many cells I want, I will use that, but they are all dedicated to it. So if I am using a 3 cells for the post cursor, then the remaining basically 5 cells I will use for DN from here. So this is 8x, I will use 5 out of 8. So this way you can maintain whatever the unit current weight which you have chosen to begin with, you can maintain that resolution throughout without any issue as such. Do you have any questions on this? The other thing is, as you keep on segmenting all these things, it is going to add your parasitic captions at the output. No doubt about it. And if you are basically hitting a high speed, then the parasitic captions makes more problem. So that thing is mostly encountered by using a bandwidth extension at the output driver. And the simplest bandwidth extension is that you use an inductor at the output driver. That is basically when your parasitic capacitance is becoming too high. So this is used for high speed CML output driver. Okay. So is there any question on the CML equalizer itself? CML equalizer, CML output driver, then I will move on the next topic. Yeah. Why can't you just segment the input pair and keep the current? Okay. Okay. No, but so what you are saying is, let me get your question right. So what you are saying is, I am always having a same fixed current source, which is, let's say, I naught, right? And I am having a different input pairs. How are you going to connect these input pairs, which can be controlled by Dn or Dn minus 1 to this current? How are you going to connect that without splitting I naught? Question is that, right? It will not be. That's what I am saying. So that is the case. If you split I naught the way I am saying that you are splitting it uniformly, then it will not be different. So means if I am having 32 cells, each cell is sized accordingly. This is I naught by 32. Either this whole cell is off or it is on. Whole cell is off. When I am choosing like 3 out of 8, only 3 cells are on. The rest of the 5 cells are off. They do not conduct any current. But if any of these cells is conducting, then for all of them, the potential is going to be the same. There is no difference. Transient will also not be different. Why? So the thing is, if each cell, think about it, right? This is very uniform, segmented, right? You are having 32 cells, each cell is always conducting only the I naught current. How the transient can be different? They are a differential thing, Dn and Dn minus 1. Which thing? Okay. No, source node is not, okay. So let me just put it this way. If you are saying that this, due to the mismatch between the Dn and Dn minus 1, this source node is not the same. So Dn and Dn minus 1 are digital signals. So I am not using a analog voltage as such. Means more or less, means Dn and Dn minus 1 all have the same input pattern, input swings. So if you say that Dn is a different voltage and Dn minus 1 is a different voltage, fine, that is right. But here Dn and Dn minus 1 are digital signals with the same signal pattern. Okay, and the only thing is these are differential, means Dn can be 1, Dn minus 1 can be 0, but in that case you are having a differential signal, so that will not create any difference in the Vx node to the extent that these cells are matched. Mismatch is a different case. Anything? Okay, so so this actually kind of concludes your CML output driver with equalization, and equalizing channel with 3 to 4 tap channel loss is common, not more than 4 or 5, because if you start using a 4 or 5 more than, then you have a more capacitance, and the thing is your output amplitude, because this is a maximum, it is swing like the supply control, so the maximum swing will actually keep on reducing the maximum amplitude which you get. So the other one which I just talked, that for a channel which is differentially terminated with a resistance 2 RT, so let me just call it V out, and we saw in one of the current mode output driver implementation that I need an I0 by 4 current to create a swing of I0 RT by 2, which is same as the swing which you are getting in a current mode output driver. Okay, so what is the easiest way to generate the same swing with I0 by 4 current on the transmitter side, which is like, let me start with this, that if I have a current this is what I need ideally to launch I0 by 4 current, and I will generate the same swing as what I am generating with the CML output driver. But the thing is, I also need a termination on the transmitter side, because the way I have drawn there, it shows no termination. Okay, so you can say, I think you have heard of this thing, that a poor man current source is a resistor. So what I will do, I will replace this current source with a resistance, which is equal to RT, so that I get a termination on the transmitter side. And if, let's say, this is, just call this as VOPTX and VONTX, right? So what I was saying is that the current is I0 by 4 going through it, so this is VDD transmitter. So I0 by 4 is equals to your VDD transmitter divided by 4 RT. Right? Means this is the simplest way I can basically get the same swing as what I was getting with the CML output driver. and I can also have a termination on the transmitter side as I have drawn. I just put a 50 ohm resistance and I have a VDD-TX. Now you see that this output swing is dependent on the supply voltage of the whatever VDD-TX I have used. Okay, so this one is equals to, so let's just write it in a different manner. So for CML output driver, current I0 is equals to your, let's say, the output swing. Let me just, so for current mode output driver, you have V output swing into I0 into RT by 2, which what is happening? Which implies that I0 is equals to 2 times V out by RT. Okay. Now for the output driver which I have drawn and which is also called as voltage mode output driver, we will see in much detail this. Your V, so let's just call that here for voltage mode output driver, your current is equals to VDD-TX divided by 4 RT, and VDD-TX by 2 is actually your V out by 2 RT, right? This is just a resistive division. So I can say that the current for the voltage mode output driver is equals to V out by 2 RT, and the current for the current mode output driver is 2 V out by RT. So actually for same output swing, I of voltage mode output driver is actually equals to I of current mode output driver by 4. So this is normally the, you can say, starting or motivation behind going behind the voltage mode output driver, that your current consumption is 1/4 of the current consumption in the CML output driver. The thing now, if I say that this also equal to the power consumption, I can only make a statement on the current consumption for the same output swing, but I cannot make a statement on the power consumption on a voltage mode output driver equal to 1/4 of the power consumption on the current mode output driver. And the reason is I am not taking the supply into account, right? So a current mode output driver can give you a same output swing, possibly with a lower supply, which the voltage mode output driver can't give. But you can say if you are using the same supply, this has the potential of going 1/4 of the power also. Okay. So now, okay. So now we see how do we implement this resistance. So simple voltage mode output driver is, let's just first draw the differential output driver so that we understand it more better. So I have so let me just make it as a channel also so that you understand. Okay, yeah. No, RT, which thing? In this, the one which I have drawn? Yeah, so this is just a drawing. Okay, we will go into detail. Means you are right that the resistance is 50 ohms and what should be the switch size? Very valid question. So the thing is, if your resistance, passive resistance is 50 ohm, the switch should be much smaller. So the switch size will become very large, right? That will put a question, why not realize the resistance with the switch itself? In that case, the switch size will be much smaller. Much smaller, right? If you are realizing a 50 ohm impedance. So that will come later, but like this is just to basically show how it works. So here you can assume that the switch is having a zero impedance, is an ideal switch to simulate for the purpose. So does everyone recognize that it will work in this manner? There is nothing, right? When your Dn is high, these two switches are closed, they are open, and the current flows in this manner. And in the other case, it basically flows in this manner. So this is the simplest way which you can implement a voltage mode output driver. Okay, now to begin, the question is, as he pointed out, that no switch can be an ideal switch. So you can say, so let's start with this. So I have to implement all these branches. So let's say we implement the left branch first, which is okay. I'm just replacing the switch by a MOS. That's what I can do. And so what we want is, we want that looking in impedance on either side should be equal to RT, right? So you can say this RT, let's say if I am calling the impedance coming from here as R MOS, so RT is equals to RP plus RP MOS equals to RP plus RN MOS on bottom side. Now if RT is equals to 50 ohm as desired, how should we basically split RP and RMOS now? So there are two things which basically guide this thing. The first one is, if I choose, let's say for example, if I choose RP is equals to 45 ohms, okay, so in this particular, RP is actually a poly resistance which will you realize in any process, okay, and RMOS is equals to 5 ohms. And in the other case, I choose RP is equals to, let's say 5 ohms and RMOS is equals to 45 ohms. What do you think will happen in the two cases when you implement these? What thing? Yeah, so let's say in this case, you have RMOS variation is lesser, right? Because you are having such a large size, small resistance, RMOS variation is lesser, but parasitic caps are a lot. And the thing to remember in all these serial links which are actually working at multiple gigabits, the problem is not only the parasitic capacitance which is going to come here. The parasitic capacitance which is going to come here is a more problem. And this parasitic capacitance is more problem because this parasitic capacitance will give you a data dependency jitter at the output. So consider when you are basically always transmitting 1, so let me just call this as CP up and this one as CP down, right? If all the bits are 1, at that case your CP is like whatever discharge potential it has gone through it, whereas your CP down is completely like to the lowest potential possible. Now as you switch between a different bit pattern like 1010 or 1100, the CP discharge may not happen to the final value, and that introduces a different crossing points or a different bit transition point at the output. So not only if I have a larger input parasitic cap that I have to use a larger pre-driver. It's not only that I use a larger pre-driver size, but it's also that the basically intermediate node capacitance create a different problem. So you see that there is a benefit in both the cases, in like benefit and drawback in both of these designs. So what is going to dominate at a given data rate and what matching do you require, you will choose a different point. So there are implementation where most of the resistance is coming from the poly resistance, because you do not want the resistance to change over process corner. If the data rate is low, you can very well go with it. But if the data rate is high, you cannot go with it because your parasitic capacitance will just limit the bandwidth. Okay. So here because I told you here that here you see that two different nodes, CP up and CP down. Okay. If I want, and this will introduce the data dependency whether you are going from high to low or low to high depending on pattern. If I want to remove that, what can I do? So you see there are this I still want to use a poly resistance and a CMOS because I need a switch, so I use CMOS. I have a poly resistance and I have a CMOS, but I want to reduce the number of nodes. Okay, so let's say so one thing is that I do not have, so if I basically do this, I do not have any resistance, and if all the resistance is coming from the MOS, then I am like having the large variation, right? I need to basically take the process variation into account. Okay, so one of the ways is you use a resistance here. So in this case you see that the two nodes have become now the one node. So here if I count here, like from the output you are having high to low and low to high, here you have make the one node. So this particular design has more often as a lesser data dependent jitter as compared to the previous one. Okay, and both the output driver which I have shown you, they are like working on the PMOS and NMOS, and these output drivers are called as a high swing output driver. We'll go in detail for this, like if what is there and more to it. Is there any questions on this? Okay, so let's stop here.